Now the shafts came from, the ones that we looked at were from the USS Chief. And here you can see the level of calcareous, the biogrowth. I mean, almost every surface that's exposed to seawater is going to have this really tough, tenacious, hard particles growing on it. However, what we can see is this is actually the bearing region. This is still part of the coating. And we noticed that there was very little buildup on that, on the coated region. And as they're pulling the port shaft away from the strut bearing, you can see these very isolated regions of biogrowth, and then you don't have any, pretty much, other than that, there's none on the coated surface. And that was really a positive thing, because even these buildup, you could take a penknife and you could chip them off, so they weren't anchored on, whereas you couldn't do that in this region. Those things are really anchored tightly. Another, this is you can see that the coating here looks pretty good. One area that the Navy was very concerned about was here. The coating is on this side, it gets feathered a little bit, and then it abruptly ends right there at that interface. And the concern was, when you put this into seawater, what happens at that interface? Does the water penetrate to the substrate under the coating? Does it produce corrosive material that has volume expansion? Will it just pop off the coating from that interface? It was really great to see that, in fact, we didn't see any of that. The coating right to the edge remained intact. So these are just various types of tests that were carried out. But to summarize what we found, there were absolutely no signs of coating spallation. And this is after 7 years, not 18 months, 7 years. And there were over 80% of the coating region showed no signs of wear or chemical degradation. So I believe that this coating could have gone back into service. However, to be safe, they removed the coating and then rebuilt it and put it back into service. So just for these MCMs, minesweepers, the return on investment cost avoidance, these are real conservative figures, around $36.5 million for the fleet of minesweepers. And the key Navy participants in the program, which includes Dr. Haverkoff and Vasudabin from ONR, as well as Bob McCaw and Ken Scandell at Naval Surface Warfare Center at Carter Rock, they won a prestigious award. I know that name, I'm not crazy about that name, Ph.D. prize, but it's actually a very prestigious award within the Navy, basically because using the technology that they helped develop, they're saving the Navy a lot of money. This is a conservative estimate of about $100 million a year. So that was a huge success. So that brings us to this topic. First non-military nanostructured coating application. And it's derived specifically from the Navy work. In 2000, I asked Dr. Haverkoff if he had any issues with my using the knowledge we gained from that Navy program for making money, applying for industrial applications. And he thought it was a great idea. So at that time, John Williams at Mobius Industries and Jimmy Walker at F.K. Gardner, both here in Houston, we got together and we decided to start a program specifically on using the knowledge gained in the Navy program to come up with a new customized nanostructured titanium dioxide coating for high pressure acid leach application. Now, the application is on ball valves, severe service ball valves. So high pressure acid leach, it revolves around the core part of the whole process are these autoclaves. And the area that, one of the areas that has a lot of these mines, hydrometallurgy mines, is in Western Australia, primarily because they have these red earth. I mean, if you're on a plane flying to Perth, you can look out the window and you can see this red desert. And a lot of that is lateritic ore. It's low-grade nickel and cobalt in all that dirt. And it's at the surface, so it's easy to mine. You can, the open pit mining, gather that. And then I guess someone had the crazy idea, let's try to dissolve as much of that dirt as possible and extract out downstream the nickel and cobalt, and try to do that economically. Well, to do that, what they do is they have hot slurry acid in here. And that slurry acid has high temperature, high pressure, and high concentrations of acid in solids. I mean, this is a materials engineer's nightmare, because there's not many materials that will withstand those conditions. And it's, I mean, think about it, they're designed to try to dissolve as much of all types of materials as possible. So this autoclave, which actually looks like a grounded submarine, is made out of titanium, or is completely titanium cladded inside, just so that it can survive this environment. One of the key components to any of these autoclaves are ball valves. And to survive this environment, the ball valves have to be made out of solid titanium, which comes at a really high cost. From my understanding, in 2000, a cost of a 10-inch bore, that's the whole size, ball valve with the coating was going for, with the actuators, we're going for over $300,000. That's for one valve. And these valve sizes range from half-inch bore size all the way to 12-inch bore size. And there are literally hundreds of these valves per autoclave. Without a protective coating, even solid titanium will start undergoing wear. And sometimes within weeks of installation, you'll start getting leakage. And if you think about the cost involved in here, this was an ideal application for trying something really different. Sometimes I wonder whether it was harder to sell these plant managers on using a nano anything in a mine like this. I mean, these plant managers tend to be quite conservative, and but we went ahead. We wanted to differentiate ourselves from the competitors, and so we told them it's nanostructured coating. And the two areas of the ball valves that require these protective coatings are the outer surfaces of the balls, and then the matching surfaces of the two seats. So here you can see the constant spraying of the outer surface of the ball. Once you spray it, you then have to grind or hone the coating, and then you polish it, and then you match slab your seats to your ball to get a perfect seal. Here are a couple examples of coating failures. In this, you can see there's gross spallation of your top coat. Your ceramic, a lot of it peels off. That could be improper spraying of the component. It could be also, in this case, due to penetration of the slurry to your substrate, attacking it, and your corrosion products are obviously has an increase in volume, and you get high strain within a ceramic and pops off. Here you either have a ball that hasn't been centered properly and has excessive wear on one side, or if your coating itself is not wear resistant enough, you can have premature wear. So in 2000, when we got together and agreed on working on this new nanostructured coating, the criteria we want to meet were that we want to have obviously sufficient corrosion resistance, wear resistance, superior toughness, and good adherence. And we proceeded to use TiO2 coating, primarily because if titanium survives, we all know that it's because of the passivated layer there. TiO2, that's really inert. And so we felt like it was a good, safe choice to go with TiO2 as our coating material. We knew it was corrosion resistant. Now, can we make it wear resistant enough? In addition to that, TiO2 has a coefficient of thermal expansion that matches titanium, which is our substrate. So that means that we would have a better, or we could reduce